Okay, perhaps we ought to start by at least some review. I just want to bring a little bit more physical example back to the lecture last time where we talked about representations and irreducible representations of the rotation group. And let me just take the hydrogen spectrum, which you all know very well, as an example. You have 1s, 2s, 3s, 2p, 3p, 3d. And if you apply magnetic field, of course, each of the P and D states would split into, say, 3 states, 5 states, and so on. But let's switch off the magnetic fields. So these would collapse back into the same energy. Now, in this case, let me just take 2s and 2p. Now, you know that 2s and 2p together form 4 states, right? Together, they are a representation of the rotation group. So if I take any state, which is a linear combination of these 4, rotate it, it stays as a linear combination of these 4. But these 4 states, or this space of 4 dimensions, is not an irreducible representation, in the sense that if I divide the 4 into 1 plus 3, then if I do rotations, these 3 stay within these 3, and this 1 stays within this 1. They don't mix. How does this imply? What does this imply about the degeneracy in terms of rotations? Let me take, for example, one state, say the m equals 1 state here, all right? And suppose it has a certain energy E. Then it satisfies this equation. Now, because, and let me call this state 2, all right? The m equals 0 state of the 2p state, let me call that 2. Now, because these belong to the same irreducible representation, that means there is some rotation operator that takes, say, psi 2 into psi 1. So a rotation on psi 2 gives you psi 1. Right? Rotation mixes these together. So I write this equation replacing psi 1 by r psi 2, where r is some rotation operator. Then I just multiply by r inverse on this side. And if I now know that the system is spherically symmetric, that means R inverse HR is the same as H. That is the statement that there is symmetry. Then you prove that H psi 2 is equal to E psi 2, namely that this state must have the same energy as that state under 2 conditions. 1, the system has spherical symmetry. That is a statement on H. Secondly, psi 1 and psi 2 belong to the same irreducible representation, irreducible. But you see, using this argument, you cannot prove that this state has the same energy as that state, okay? Because there is no way by applying a rotational operator you can take any of these states to any of these states. They do not belong to the same irreducible representation. Therefore, the fact that 2s and 2p have the same energy has nothing to do with rotational symmetry. They do not belong to the same irreducible representation. It is an accident, okay? Now, you can always explain that accident by some other symmetry, which is very special. I won't discuss that. It's very special in the case that it's easily ruined and nothing to do with spatial symmetry and so on. This has to do with the conservation of the lens vector. Right? I just want to, therefore, make a connection between 2 points. One point is the rather mathematical concept that distinguishes a representation from an irreducible representation, and to relate that to this physical example, which you know very well, that 2s, 2p have the same energy, but this is accidental, has nothing to do with rotational symmetry. But within 2p, the fact that the 3 states have the same energy is deeply related to rotational symmetry. And of course, by the theory of irreducible representations, you know that these must become in multiplets of 3, 5, 7, and so on, 2L plus 1 multiplicity. So that's just a bit of addition to the lecture last time. Now, we're still ahead of time. So before I launch into today's lecture, I want to talk about a question that was raised by one of you 2 lectures ago. And I gave sort of an answer, which was actually correct, but I don't think you caught it all because it was rather brief on the blackboard. So I want to go through this rather more carefully today. And all this, in actually slightly more detailed form, is posted on the course web page. Right? And you can download the whole text for this discussion. So let me start by essentially rephrasing your question, all right? To rephrase the question. This goes back to when we were discussing translation and rotational operators. Now, if I do a translation in Cartesian coordinates, so I change x by a certain amount, we know that that is generated by an operator that goes like this, right? It's the exponential of something with c and the momentum operator. So we say this thing is the generator of rotations, okay? Or you can say px over h bar, never mind, all right? So px is the generator of rotations. Now, of course, this just comes from a Taylor expansion. And at the end, of course, you recognize that px is also the conjugate momentum to x from just the classical Lagrangian. So that's nice. Now, we next did rotations. So I rotate about z. That means I add a certain or subtract a certain amount to the azimuthal angle. And you find that the corresponding rotation is related to jz. So the generator is jz. That's something we found. Now, at the end, of course, this is, I think, your question. The generator that you find happens to be the conjugate momentum that corresponds to this phi. Right? Now, is this an accident? So, in a sense, it's the conjugate momentum in the sense that, this should be jz, sorry. All right? This jz happens to be the partial derivative of L with respect to phi dot. So this leads to the question, how can we guarantee in general that if I displace a generalized coordinate, which I call capital X, all right? In the above example, it will be phi. The generator is the corresponding generalized conjugate momentum P. Right? I think that is one way of stating your question. Okay? Do you understand why there is a question? In the above example, it seemed to happen that it was J, right? And it agrees with the conjugate momentum. How can you guarantee that it always agrees with the conjugate momentum? So that is the question you pose, and that's actually a very important question. So I will present the argument in 3 steps. The first step I will prove is that a generalized coordinate and its conjugate momentum satisfies the canonical commutation relation. Now, because this is not for me to say, okay, I can say x and px commutated as IH bar, y and py. I can say that in Cartesian coordinate. Then any other commutator must follow as a consequence. I cannot separately postulate other commutators. Do you understand? Because everything is built up of x and p's. Okay? For example, if I say x and px commutate as IH bar, then whether phi and jz commutator is also IH bar, I should derive. I cannot no longer assume. Right? So how can I derive that this is the case? This will be actually the meat of the calculation. Once you have this, of course, that means P can be represented by this operator. It's just a derivative with respect to capital X. And that will mean that the generator for translation in capital X is just capital P. So I will just argue in 3 steps. The first 2 steps are actually more general questions, have nothing to do with translations. And in fact, you can state it in the following form in the bottom bullet, that canonical quantization is invariant with respect to coordinate transformations. Okay? So a sort of analogous statement is to say, these 2 vectors have, these basis vectors have dot products delta ij. Right? Once I say what the dot products are, I have defined the inner product over all space. Under a rotation of axes, can I guarantee that these basis vectors also have dot products delta ij? I cannot postulate that independently, right? Because I can always reference, say, 2 of these vectors into the original basis vectors. And I can therefore calculate their dot product. It is something I need to calculate and prove still is delta ij. I cannot separately postulate, okay? And it is exactly the same idea. This statement is that dot products are invariant with respect to rotations. And this statement is that the canonical commutator is invariant with respect to coordinate transformations. Generalized coordinate transformations need not be linear. Okay? So that is the problem that we set ourselves. So let's try to do this. So I start off with the Lagrangian in x and x dot, and the canonical momentum is p. And the quantization is obtained by imposing this condition. All right, xipj is I h bar delta ij. That's where I start, and that shows that pj can be represented as this derivative. Now I change to some generalized coordinates, which I call x alpha, capital X alpha. Alpha, of course, runs over the same range, say 1 to 3 or whatever, all right? But I use index alpha to denote the generalized coordinates. I can always rewrite the Lagrangian in terms of capital X, and the capital P is defined in the usual way. If I were to do canonical quantization on the generalized coordinates, I would impose this condition. But of course, it's really not for me to impose. So how can I guarantee that 8, which is this equation, is consistent with this equation? Okay? In fact, we are only allowed to impose one quantization rule, say this one. So we need to derive this one as a consequence of this one. Okay? So I start with this one. I want to derive this one, where capital X is a generalized coordinate. And I will not give the general proof. I will give it for a special case, but still highly non-trivial case, where at least in terms of the original coordinates, the Lagrangian takes this form, that there is a kinetic energy which is quadratic in the velocities, but I allow the coefficient to be A, non-diagonal, and B, dependent on position. Okay, so that is a substantial generalization. You can imagine things that are slightly more general and the proof becomes a little bit more complicated, but the idea will be the same. This is a sufficiently non-trivial example. Okay? Certainly includes the obvious one where Mij is diagonal and constant, which is the usual kinetic energy. Now, if this is a Lagrangian, then by taking the partial derivative, of course, the momentum is just Mij xj dot. In matrix form, P vector is M matrix times velocity vector. Okay? So let me try to relate the velocities. The velocities in terms of the old coordinates is just a derivative of the old positions. I use the chain rule. I differentiate the old coordinates with respect to the new coordinates, and then the new coordinates with respect to time. Of course, sum over alpha implied. This set of partial derivatives I simply write as a shorthand as a matrix AI alpha. That is the matrix of transformations between the two sets of coordinates, and then the velocity capital X alpha dot. Now, notice one thing. Because we are talking about velocities, right? These are velocities. We are concerned about velocities. Velocities have to do with infinitesimal displacements, right? It's dx upstairs. And the infinitesimal displacements satisfy linear transformation properties. By this, I mean the following. No matter how complicated this function is, this function is linear. Okay? That is the definition of A. The derivatives, the differentials satisfy linear relationships, even if this is a nonlinear relationship. Okay? And that we have that simplification because we are talking about velocities which relate to infinitesimal displacements. Okay? So if that's the case, if little x dot is A times capital X dot, and you go back to this expression, right? So you have an expression that goes like this. I won't write the half. It's a matrix x dot, and x And in fact, if you write it in matrix form, it actually should go this way. X dot transpose, okay? So X dot is A capital X, and this transpose is A transpose capital X transpose. So this is, I call capital M, right? So the Lagrangian, the kinetic term can now be written as capital M, capital X dot, where capital M is A transpose MA. So a new mass matrix. And if you have this form, then capital P is capital M times capital X dot, right? By just doing the, using the definition of capital P on this one. Now, I want to write the inverse relationship. Let's see. Little x dot is A times capital X dot. I just want to invert this relationship. I write capital X dot is B times little x dot. So B matrix is the inverse of A matrix. Okay? Why do I want to do this? Because from this expression, capital P is M capital X dot. Then I put this capital X dot in. So I have M, B, little x dot, okay? But I also know that little p is little m, little x dot. So I invert this relationship. Little x dot is M inverse P, okay? Everything, all the indices become simple if you think of these as matrices. So this little x dot is M inverse little p. Okay? So that's capital P. Now I want to calculate the commutator between a capital X and a capital P. Now, don't worry about the indices, all right? Go home and check it out. They all work out if, if you think of them as matrices. So I have an expression for P, which is a bunch of stuff times little p. All right? This relationship, you see, I have related capital P to little p, okay? So I now want to express everything in terms of the little x and the little p. So capital P is this stuff times little p. But all this stuff is a function of position only. So it commutes with this position. So I pull it all out, okay? So it's capital X commutator little p. But capital X is just a function of little x. So any function of little x commuted with P is df dxi xi pj. Okay? So I put that in. You see this derivative, this function differentiated with little x is just this derivative. Okay? So capital X commuted with capital P is derivative of capital X with respect to little x commuted with P. That derivative is just a B matrix. So you have a bunch of matrices, this commutator. This commutator, of course, I know is just IH bar delta IJ. So I have IH bar. I write that J as I. J as I. And if you look at this carefully, this is just the alpha gamma entry of this product matrix. Okay? Because M, you start with M, alpha beta, B beta K, M inverse Ki, and then I write this back here as B transpose I gamma. Okay? But that product matrix, remember that capital M is just A transpose little m A. Is then this product, but you see this product is identity because AB in the middle is identity, cancelled. M and M inverse cancel. And then A transpose B transpose is the identity. All right, so you work it from the middle out. So this is identity alpha gamma, in other words, delta alpha gamma. So that proves, oh, I must have goofed something. I must have goofed some indices. This cannot, if this is gamma beta, this cannot be alpha gamma, right? I must have goofed some indices. You check it out, okay? So if X commuted with P is IH bar times the Kronecker delta. That means the P can be represented by this. Okay. Now, this whole argument, although I have written it in terms of canonical commutators, you can actually phrase it entirely in terms of Poisson brackets. That is, no H bar, no I, just Poisson brackets. Okay? So this is actually a theorem in classical mechanics, really, that Poisson brackets are invariant under generalized coordinate transformations, sometimes called contact transformations. Actually, contact transformations are slightly more general. They can even mix X and P. Okay? So if I now translate a generalized coordinate, say by this amount, the generator is obviously this generator. This is just Taylor series. Okay? Nothing more than Taylor series. So, but because I have derived that capital P is related to this derivative, I can write this operator as this thing. And that, of course, shows that the generator for translation of capital X is just exactly capital P. Okay. Now, a slightly formal derivation, but since the question is rather formal, that has to be the answer. Okay. I'm not even sure this is the simplest possible proof, but that's the main idea. Right? And that's why, actually, in the old days, when people spend much longer time studying classical mechanics, these theorems, contact transformations, is a whole chapter in, say, Goldstein, that Poisson brackets are invariant with respect to contact transformation and so on. Right? It's all that theorem in classical mechanics. Okay? Any questions? Okay, if not, let's see. This one. Okay. So today we start with internal symmetries. Okay. Last time we talked about rotational symmetries, which is you do a rotation in space, and at the end of the lecture, we found that rotations in space can always be represented as changing an up state and a down state. Spin up, spin down. I also showed that angular momentum 1 can be regarded as spin up, spin down, say that this state. Mathematically, you can make up a spin angular momentum L equals 1 object as 2 spin up, 2 spin down, or 1 up, 1 down. Now, I'm not saying that orbital angular momentum is physically due to spin. I'm just saying that these two things are mathematically the same. Okay? They have the same transformation properties under the rotation group. So you can use this fundamental representation of a single spin to understand everything about angular momentum. And roughly the same idea will be used when we talk about internal symmetries. So today will actually be a fairly simple lecture mathematically. I will just introduce the topic of isospin in the context of nuclear physics. I haven't given many examples here, but you can go back and look up any book on nuclear physics for examples. Then I will generalize this to quarks and flavor, and then quarks and color. And then I will give you, the last bit will be slightly mathematical. I will give you the formal mathematical structure of SUN, which is captures most of the important groups that we talk about in particle physics. Right? And I will, in the course of that, explain what is meant by S and what is meant by U. So let me start with the idea of isospin in the context of nuclear physics. Starting with some physical observations. The physical observation is very simple, that the proton is nearly the same as a neutron, except for charge. Except for charge means except for the electromagnetic interaction. If I don't worry about the electromagnetic interaction, charge is irrelevant, and the electromagnetic interaction is actually rather small compared to nuclear effects. And the typical order magnitude is related to the fine structure constant, 1 over 137. So sort of at the 1% level, you can ignore EM effects. And if I ignore EM effects, the proton and the neutron seem to be the same. Okay? So in fact, let me imagine I switch off EM. That is, I set alpha going to 0. Then the postulate is that in that limit, the proton and neutron would be exactly the same. Like a spin-up electron and a spin-down electron when there is no magnetic field. Okay? They are the same. You can just do a rotation and change one to the other without changing the physics. And just to illustrate to what extent they are the same, if you look at their masses, one in terms of GeV, one is 938, the other is 939. Right? So they differ actually by only 0.1%, not even 1%. That is the level of accuracy we are talking about. So to start off, any symmetry that we talk about in terms of nuclear isospin will only be an approximate symmetry. It's not an exact symmetry. All right? When we say things have the same energy or whatever results we derive would only be approximate to sort of this level of accuracy or 1% or something. So going back to rotations, the rotation group involves a set of transformations, which we can imagine is changing spin up and spin down one into the other. So we change spin up to spin down or vice versa, and they are described by Jz having values a half or minus a half. That's just changing. Rotation symmetry means that in that change, the physics remains the same. Okay? So in exactly the same thing, we now introduce a concept which we call isospin. The isospin group is obtained by changing a proton into a neutron or vice versa. And the proton is called isospin up, and the neutron is called isospin down. And I use the notation T. So Tz is equal to a half, and Tz is equal to minus a half. Okay? And in fact, you remember that in rotations, you also have J plus, which changes, say, a spin down to spin up. So in exactly the same way here, I have a T plus, which changes a neutron to a proton, and so on. Okay? So it's exactly the same structure. Now that is the group, and isospin symmetry means that physics remains the same when you flip these isospins. Flip isospin spin is just another way of saying interchanging proton and neutron. And isospin symmetry is only approximate to about order alpha, in exactly the same way as rotation symmetry can also, in some cases, be approximate. For example, if there is a magnetic field, these three states would be slightly split. So mathematically, it is exactly the same. Exactly the same group structure. In the spin case, you talk about three generators, JA, which can be X, Y, Z, or Z plus minus. In the isospin case, you have operators which we call TA. T is called the isospin operator. And here, spin up, spin down corresponds to proton and neutron. So you just copy everything over. Right? So that is the isospin group. Okay? I don't have offhand recall examples, but let me just quickly do one. Suppose you have proton and neutron. Now suppose I have two of them. I have a state of two nucleons. Nucleon means either proton or neutron. So I have an A equal to 2 system. A is just the atomic mass. The mass number is the sum of the number of protons and number of neutrons. So how many states are there in terms of isospin structure? There would be 4, right? So PP, PN, NP, NN. Right? So there are 4 states. These 4 states form a representation of the isospin group. Isospin simply means I change proton to neutron and so on. So if I start with 2 of them, no matter how I change, I can't get 3 protons. Right? So the A equal to 2 sector is closed under isospin transformations. So this is a representation. But it is not an irreducible representation. In fact, we don't have to do it all over again. We just copy what we learned in rotations. This representation breaks up into two sets. One is PP, Pn plus Np, Nn, and then the top three is an irreducible representation. The bottom one is in an irreducible representation. Isospin symmetry would guarantee that these three have the same energy, but would not guarantee that these three would have the same energy as this one. Okay? And if you have this state, then isospin symmetry guarantees that you must have this state and this state. So this is called an isospin triplet. Total T is equal to 1. This is called an isospin singlet. Total isospin equal to 0. Just as you talk about L equal to 0, L equals 1. Okay? Do you know what are some of these states? Do you recognize some of these states? Have you seen any of these nuclei? Simple question in nuclear physics. What A equal to 2 nuclei do you know? Huh? H is A equal to 1. Huh? Deuteron. So, which is a deuteron? Yes. Well, certainly it's not this one, it's not this one, because it is 1p and 1n. Okay? So it's either this one or this one. Okay? Which one do you guess it would be? Now, this is actually very tricky. The intuitive answer is actually wrong. Now, suppose isospin is exact, which is not the case, all right? It's only to about 1%. If the new deuteron is this guy at a certain energy, then there should also be this state and this state at the same energy, right? If isospin is exact. What is this thing? What is this thing? If it exists, what would you call it? Oh, come on. This is something that high school students should know. If I give you the constituents of a nucleus in terms of proton and neutrons, you must be able to give me the name. Huh? Helium-2. Does helium-2 exist? Now, if isospin symmetry is exact, and the deuteron is this one, then helium-2 would have exactly the same energy. Okay? I think, now I don't remember, I was trying to look up this morning, I didn't have time. I think deuteron is this one. Because the naive answer, because you know there is no helium-2, right? That means this thing must have a positive energy. Okay? If it's negative energy, it's binding, then it's stable. Then you would guess deuteron is this one. If deuteron is this one, then it would have no partners. But I think that's not true. I think deuteron is this one. What happens is that the deuteron, which is equal to the symmetric one, has an energy. All right, let me. This is the zero binding energy. All right. That is just below the sum of a proton plus a neutron. The mass of a deuteron is just a tiny bit less than the sum of the two individual masses. So it has a tiny binding energy. Okay? So this is the deuteron. And PP and NN are both slightly up there, I think. Okay? So this is actually a multiplet. that difference is at the 1% level. It's the level of the breaking of isospin symmetry. But it so happens that the binding energy is even smaller. So that 1%, or whatever it is, fraction of a percent, just crosses the threshold between binding and not binding. And so you bring two protons together, they don't have a binding energy. They don't stay together. So helium-2 is a state. It is a state, but it's not a stable nucleus. Okay? It's an excited state. Right? And well, this NN, you won't even have a name for it. So how do you actually distinguish between this one and this one? You have to look at the wave function in detail. Okay? You have to look at the wave function in detail. Let me see if I remember. Yeah. In fact, the argument goes as the following. Do you know what's the spin of deuteron? The total angular momentum of deuteron. Angular momentum is 1. Okay? So it's spin, not isospin. Because proton-neutron also has a spin, right? Spin up, physical spin, angular momentum. If it has angular momentum 1, that means the spin wave function is, oops, I better not say, I'm not sure. You look it up, but I'm pretty sure it is the symmetric one. Now, this is actually only the simplest example where you have total T equals 1. You can imagine cases where you have, 15 protons and neutrons, A equals 15. There will be several possible states, right? Okay. So they are what's called, they are not isotopes, they are called isobars. They have the same A, okay? Like helium-2 and deuteron, even though one of them is not stable. There are cases, if you go high up, where several of them would be stable. Okay? And so you can relate different nuclear states using the concept that isospin is an approximate symmetry. Right? Now, this is a large field in nuclear physics. I won't go into the details. And you can actually do better than saying that it is symmetric under isospin, because that would be only sort of at the 1% accuracy. You can actually study the breaking of that symmetry. Just as for the spectrum of hydrogen, you can study the regularities of the Zeeman effect. If I have a magnetic field that break apart the 3 2p states, what the pattern of that breaking is, you can actually work out, right? So you can, with a bit of more information, you can work out the pattern of these breakings. Okay? So that is isospin. So here we have a case where we have two objects, proton and neutron, which you exchange. Okay? Now, either you regard them as identical, then the result is a symmetry, or you regard them as approximately identical or similar, just only similar, then you have an approximate symmetry. So you have two types of things that you can exchange. Then you have a symmetry. This symmetry is called an SU2 symmetry. 2 means there are two objects being exchanged. Okay? Now, I will later explain what is SU. So it's easy to generalize this idea. If you have n objects which can be exchanged, then you have an SUN symmetry, which can either be an exact symmetry, if this exchange absolutely does not matter, or it could be an approximate symmetry if the exchange is nearly the same. The n objects are similar, but not identical. Okay, so this is just a very simple idea that generalizes two steps. One from rotations to internal symmetry, and then from two objects to n objects. Okay. So let me give you an example of three objects which are nearly the same. Now, this is an example of three objects that are nearly the same. And I have to give you some background about quarks. You know, elementary particles are two types. One are baryons, one are mesons. Baryons are like, let me But I now realize that these terms may not be familiar to you. Baryons are things like protons, neutrons, and their excited states. Mesons are things like pi mesons, rho mesons, and so on. Okay? These all have antiparticles. These carry baryon number equal to 1. And antiproton, antineutron carry baryon number equal to -1. Baryon number is conserved. Okay? Mesons carry baryon number equal to 0. Okay? Now, we now have very good evidence that baryons are made up of 3 quarks. And mesons are made up of 1 quark and an antiquark. We write QQ bar. So to understand what kind of baryons there are and what kinds of mesons there are, we just try to understand what kinds of quarks there are. Now, by now, there are hundreds, I don't know, 200, something like that, maybe 200, increasing every day. How many types of baryons and mesons have been discovered? Most of these are unstable, live a very short time, but they still exist during that time, and they are particles. They are listed in particle tables, right? So a large part of elementary particle physics is to try to understand this whole zoo, these hundreds of elementary particles. And by the time they get to be hundreds, of course, you don't regard them as elementary. You look at even more fundamental constituents. So now, when we talk about particle physics, people talk about quarks. They try to understand quarks. Okay? And it turns out that quarks, there are only 3 types, which are called 3 different flavors. Well, actually, there are 6 types, but I will only, the 6 types actually are grouped into 2. Okay, they are called UDS CTB, something like this. All right, I will talk only about these. These are called the 3 light quarks. These 3 are called the 3 heavy quarks, and they can be sort of to some extent separated. So I will talk only about the 3 light quarks, and a large group of these baryons are made out of the light quarks, right? So instead of talking about hundreds of baryons and mesons, I only talk about 3 quarks and 3 antiquarks. And everything is made up from these things. Now, these quarks have a very strange property. Their charges, electric charges, are 2/3 or -1/3 unit. A unit is, the absolute charge of an electron. And the quarks are approximately the same. Quarks of different flavors are approximately the same. So this is an approximate symmetry. So let me list the 3 quarks for you. Here are the names of the 3 quarks. They are called up, down, and strange. All right? And the electric charges are 2/3 and -1/3. There is also another quantum number that labeled them. It's called the strangeness, capital S, which is 0, 0, -1. And these are called the 3 flavors of quarks before the heavy quarks were discovered, right? Okay? Any questions?
In what sense are they approximately the same?
They have nearly the same mass. In their more importantly, their interactions. The interactions is invariant with respect to this group. Okay? In fact, the Lagrangian that people write down to describe this thing, the only symmetry breaking term is in the masses. That's typically what people believe. Okay. So let me give you 2 examples of the states that you can make. A proton, we believe, is made up of 2 U's and a D. So let's just check the charge. Charge would be 2/3 plus 2/3 -1/3. And this integer, 1. A neutron is made up of 1 U and 2 D. Okay? And the charge would be 2/3 -1/3 -1/3 is 0. Right? And the fact that the proton is nearly the same as the neutron is now traced to an even more fundamental fact, that the U is nearly the same as the D. All right? Let me see if I have. So typically we draw this in a triangle, UDS in the following way, and interchange among these three, or we say interchange of the different flavors, is an approximate symmetry. And it's called SU3. To distinguish from another SU3 later, I sometimes use a subscript F to say we are talking about flavors. Now, let me go back and pose something that may seem like mystery to you. If proton and neutron are like this, shouldn't there be another state with UUU and another state with DDD? Also at the same energy, because if I can switch it, right? Okay? I mean, that's a natural question you would ask. Just like, if you have a certain spin multiplet, you find the middle few, you should apply the J plus operator. If I use an operator that changes a D to a U, I should get this one, and should have the same state, same energy, right? That may seem like a natural question to ask. I will come back to this a little bit later. Okay. So that's an approximate symmetry. And actually, to answer this question, you have to write out the wave functions more precisely. And that is actually more complicated because you have to consider the spin at the same time. Because actually, we are not talking about just three things, but 3 times 2 things. You can have U spin up, U spin down, D spin up, D spin down, S spin up, S spin down. Actually, all 6 things have to be permuted. And in writing these, actually, this have mixed symmetry. Their particle identities is not totally symmetrical and not totally anti-symmetrical. And their spin structure is also not totally symmetrical, not totally anti-symmetrical. So the whole thing is a little bit messy, so I won't discuss this. But I can discuss another example where everything is symmetrical in the following sense. All the spins are symmetrical. So you can imagine them, all 3 guys pointing up. Okay? All the UDS identities are also totally symmetrical. Then you can look at each sector independently. In that sector, actually you do have this multiplet. Okay? This is called the delta. And what would be the charges? 2/3, 2/3, 2/3, so 2 units of charge. 2/3, 2/3, 1/3 is 1 unit of charge, 0 minus. So there are the delta particles, which come in 4 different charge states: double plus, single plus, 0, and minus. Now that is a bit strange when it was first encountered. This was discovered in the, early 1950s. The energy is about 1.283 GeV. And the energy difference among these 3 is very small, just like the energy difference between proton and neutron, right? 939 versus 938. So typically people don't even list the difference. It's strange in the sense that the charge range goes from +2 to -1. If you think about it, that's actually not all that strange, because you look at proton and neutron, it's not symmetrical either. It goes from +1 to 0. Later, people discovered 3 other particles. Now, these are made up with 0 s quarks. If I now allow you to use 1 s quark, what can you make? Well, the other 2 can be either P or N, right? So in fact, U or D. So it's UU, UD, and then DD. Okay? And these, if I remember the names correctly, are called sigma. Sigma plus, sigma 0, sigma minus. Okay? Suppose I allow you to use 2 S's. Then there are only 2 possibilities, U or D. And this is called the Cassi. sorry, C0 and a C minus. Now, these masses are slightly different in the sense that the mass of the S quark is slightly larger than the mass of the U and D quarks. So there are two levels of approximation. At the crudest approximation, you say all three have the same mass, then all this bunch have the same mass. At the next level of precision, you say that the S quark is a bit more, a bit heavier than the others. Then each row, lower row would be heavier, right? Because each lower row, you replace a U or D with a heavier quark S. That was the experimental situation in the early 1960s. Then Gell-Mann predicted that there should be another one, which is SSS, and that is the omega minus. Okay? And he was able to predict the mass, which you just go in equal steps. Okay? If I remember correctly, this is about 16 something. Okay? Actually, when he first discovered this, he did not use the quark language. He did not dare make the assumption that they are these fundamental objects with fractional charges. That is so much against conventional wisdom. He used the abstract group theory to arrive at this. Okay? So this is an example where you have three types of objects, U, D, and S, regarded as approximately the same. Then this is an irreducible representation of the SU3 with multiplicity of 10. Okay? That's actually a very simple representation, which you can write down quite easily like this. All right? This is a 10-fold representation of the SU3 group, a very important example in the history of the classification of the elementary particles. All right? So, and all these have symmetrical spin wave function. Actually, for example, it could look like this, right? U up, U up, U up. Now, let me talk about another aspect of quarks, which in a sense is more important. Now, each quark actually, we now believe, also comes in three colors. Now, colors and flavors are just names, all right? It just means there are 2 degrees of freedom. So you have the U quark, D quark, and the S quark, and these are called different flavors. But then each of them could be either red, green, or blue, and these are called the different colors. So actually you can have a U quarks that is red, a U quarks that is green, or a U quark that is blue. So you can do 2 things. You can swap among U, D, and S, right? So you change the different rows. You change a U to a D. That means a UR changed to a DR, and so on. That is what we just discussed. That is the SU3 of flavor. Or you can swap these, change R into G or G into B, and so on. This is called the SU3 of color. Okay? So that is another group. Now, interchange of different flavors, the SU3 of flavor, is an approximate symmetry. This is what I have discussed here. But the interchange of different colors, that is interchange of red, green, and blue, is an exact symmetry. And in fact, the world has to be a color singlet. This is a dynamical rule. Singlet means it always combines like this one. Go back to the case of spin. If you have 2 spins, then you can combine into this one, which is a spin singlet. It has angular momentum 0. So color, you can also combine in such a way so that it has total color equal to 0. 0 means if you take any color operator operating on it, you get 0. Okay. And this is called the SU3 of color. And gauge theory, or Yang-Mills theory, which we are going to talk about later, is related to the SU3 of color. And the quantum theory is called quantum chromodynamics. Chromo just means color. This is an analogy to quantum electrodynamics. And normally we say QCD, just as quantum electrodynamics is called QED. And the physical state has to be an SU3 color singlet. Okay? So that is a bit of a physical introduction. With that, let's come to some mathematics, the formal structure of SUN. In other words, in quantum mechanics, how do we describe interchanging n particles, n different types of particles? What is the mathematical and group structure? So if you have n different objects, I can write the n different objects as n different states, psi 1, psi 2, all the way up to psi n. And I can represent them as column vectors. The first one as 1, 0, 0, and so on. The second one as 0, 1, 0, 0, and so on. So this is a column vector of size n. And a general state would be a linear combination of these basis vectors. When I say I can change any of these, I means I can operate on one state to get another state using an n by n matrix, right? Because that's the most general linear transformation possible. The most general linear transformation to change one state in this space to another state in this space is by an operator U. That is the formal statement of changing one of them into another of them. Okay? Example, n equals 2. Change proton into neutron. Or something more general, it is just an operator operating on one state, giving you another state. However, this operator has to satisfy certain conditions. The most important is that it must preserve the inner product. That if I have two states, psi and phi, and I operate to get the new ones, then the inner product of the new ones must be the same as the inner product of the original ones. Remember our discussion earlier with respect to translations. I have one-way function, two-way functions, all right, like this, and I translate the two of them there. So the inner product between these two must be the same as the inner product between these two, right? The inner product is preserved during the transformation. So the same idea, phi bar psi bar has to be equal to phi psi. So I just apply these two equations. Psi is u times, psi bar is u times psi. Phi bar is u times phi. But of course, since I flip it to a bra vector, this one has to be the Hermitian conjugate. If this statement is true for all states phi and psi, that means u dagger u must be equal to the identity. Okay? So it's not all arbitrary linear operators u, but only those u's that satisfy u dagger u equal to identity. And all such operators are said to be unitary, and the group of all such unitary matrices is called the unitary group in n dimensions. And it's called UN. Right? So it's the group of all n by n matrices that are unitary. Now, actually, there's something I have assumed, which I need to prove, and that is it a group? Now, certainly, if I take two n by n matrices and multiply them together, I get another n by n matrix. So that's okay. The n by n property is okay. But is the unitary property okay? If I take two unitary matrices, multiply them together, is the end result still a unitary matrix? Otherwise, they would not form a group, right? So that's easy to check. If I take u times w is u times v is w, and uv are both unitary, I calculate w dagger w. That is the dagger of u times v. But you know, when you take the Hermitian conjugate of a product, you take the Hermitian conjugate of each factor, but in reverse order, right? So uv dagger, whole thing dagger, is v dagger u dagger. But u dagger u is identity, so that cancels, and then v dagger v is the identity. So w dagger w is the identity. Okay? So the set of all unitary operators indeed forms a group. Unitary also means that the inverse is just the Hermitian conjugate. So that is what we mean by UN. As with the case of translations and rotations, it is very usually convenient to write this unitary operator as e to the I times another operator, t. And as before, you can show that t is Hermitian. Okay? So instead of talking about the unitary operators u, I will talk about the Hermitian operators t. And the proof of that is the same as in rotations. In fact, it is enough to talk about infinitesimal transformations. That is, u is written as e I theta t, where t is a Hermitian operator and theta is a small real number. So this is approximately equal to 1 plus I theta t. So departs from the identity only by a small amount. Because if I understand the small transformations by just building these up, applying these in succession, I can get all the other transformations. Okay? So if I do two such transformations in succession, u1, u2, and expand to first order in theta, you have t1 plus t2. Okay. So the u's multiply, they form a group, usually called a Lie group, but the t's, they add, okay? When the u's multiply, the t's add. So the t's actually form a linear space. So the operation among the u's is one of multiplication. The operation among the t's is addition. So they form a linear space. However, because u is given by e I theta t, if you go beyond first order in theta, the order of the t's will matter. Okay? T1 times T2 is not equal to T2 times T1, because if you multiply, say, e to the I theta T1, e to the I theta T2, this will generate a term to second order involving T1 times T2, right? Which is not the same as T2 times T1. Okay? So if you go to second and higher order, you have to worry about the order of the product of t's. So I need to consider the commutator among the t's. So the mathematical structure for the t's, there are two elements. One is you simply add them. So that is just like a vector space you can add. So that's a vector space. But also you have to commute them. You have to consider that commutators. And when you have a commutator structure, it is called an algebra. And it's called the corresponding Lie algebra. So for UN, or later when we discuss SUN, we have to consider the algebra of commutators. Now this may sound abstract, but just think back to the case of rotations. The t's are just the j's. Okay? The u's are just the rotations. The infinitesimal rotations are described by the j's. So the j's can be added. You can take linear combinations. That's the vector space aspect. But you also need to worry about the commutator among the j's. Now, the t's, first of all, form a linear space. Why? Because it's very easy. T is an n by n Hermitian matrix, right? So when you add two of them, you get another one. You multiply by a real scalar, it stays as an n by n Hermitian matrix. So it's a vector space, right? So if there, how many independent ones are there? Let's count. If you have an n by n matrix, then all these are real, right? Now these and these are related. They are complex conjugates of each other. But for each one of these involves two real numbers. The off-diagonal elements are complex. So if this is alpha plus I beta, this is alpha minus I beta. So the number of real parameters is n squared, right? Because there are as many real parameters as there are matrix elements. Each diagonal matrix element is a real parameter. Each parameter in this corner is one complex number, in other words, two real numbers. So you can think of these two together as costing you two real numbers, right? So they are exactly n squared real numbers. So this vector space has dimension n squared. There are n square independent such matrices. In fact, I can easily write down what these matrices are. One of them would be 1. So write all the possible diagonal ones with a single 1. And then I can write the following. Say with a 1 here and everything 0. So in the 1, 2 entry, I have a 1. Or in the 1, 2 entry, I have I and minus I. Okay? And you can do this for every off-diagonal entry. For every pair, you either write 1 and 1 or I and minus I. Okay? So, of course, there are n square of these matrices. Because if you choose 1, 2, you get 2 of these. Right? And they are linearly independent. Okay? So I form a basis of such matrices. I call them T sub A. So this is, if you like, this is T1, this is T2, and so on, and all the way up to Tn squared. Okay? Are the basis matrices. And but I always do a transformation such that, in fact, I will do the following. I take T0 to be the identity. Okay. So this would be n squared minus 1. I do the counting from 0 to n squared minus 1. Oh, sorry, a typo. So somebody copy for. This is n squared minus 1. Okay. The leading one I always take to be the identity. That's just a matter of convention. So any matrix T can be written as a linear combination of these basis matrices. Have we seen this before? Well, this is actually an obvious generalization of the 2 by 2 case, where you have I, sigma x, sigma y, sigma z. So this is T0, T1, T2, T3. Okay? For the 2 by 2 case, those are the independent matrices. Just write it out. This one is 1, 1. This one is 1, minus 1. This one is 1, 1. This one is minus I. I'm not sure about an overall minus sign here. Those are the Pauli matrices plus the identity matrix that we learned about. Okay? Now, since these matrices form a vector space, now this may confuse you at first. I mean, normally you think about vectors and matrices as different. But these matrices themselves form a vector space in the sense that you can add them together, you can do scalar multiplication. So on a vector space, I can try to define an inner product. Okay? And I define an inner product between two matrices as the trace of their product, of their matrix product. Well, yeah. You can check that this satisfies all the rules you need for an inner product. It's linear in this guy, it's linear in that guy, and it's a real number, okay? Because the trace of two Hermitian matrices, the product of two Hermitian matrices is still Hermitian, I think. And the trace of a Hermitian matrix, you just take the diagonal entries are real, okay? Now, there is some arbitrariness in choosing the basis, right? I mean, I can choose, instead of 0, 1, I can choose a 2 here if I want to. Right? I can choose a 2 here. So that is the arbitrariness in choosing a basis in this vector space. And I will choose a convention where the basis is orthonormal under this inner product. That is, I require that the trace of two different basis matrices is delta AB. Now, sometimes people, for convenience, choose 2 delta AB. The 2 comes up about, see, because if you look at these are 2. Okay? You take the product of this with itself. The trace is 2. Okay? So that's only a matter of convention. Okay? So let's just recap everything. U can be written as e to the it. In other words, it is just a log of u. And T as a Hermitian matrix can always be expanded as a linear combination over the basis matrices with parameters theta A. Okay? So this is called the group UN. And it's actually very much like rotations, where the rotation operator is e to the I theta A J A, where A is 1, 2, 3. Okay? Any questions? Now, you may now raise the following query. It's actually not quite like rotations in the following sense. Even if I take n equals 2, that is not quite like rotations. Because if I take n equals 2, there are 4 terms here. There are only 3 terms here. What is missing? What is missing is the 0 term, which is e to the I theta 0 times the identity, right? For the n equals 2 terms, it actually relates to this. This is sum over 1, 2, 3. The second factor is the rotations. The first factor is just an overall phase, right? It's just multiply everything by an overall phase. And the identity, I don't even have to write. Identity is nothing. Okay? It's just an overall phase. So this suggests to you that in here, I should separate out the 0, which is just an overall phase and has nothing really to do with mixing the different vectors, and only consider the rest, which has dimension 1 lower, n squared minus 1. This is just like in the rotation case when you consider 2 by 2 Hermitian matrices, like spin. You separate the identity from the 3 Pauli matrices. All right? 2 by 2 Hermitian matrices, there are 4 independent ones. But it is useful to separate the identity out and just consider the rest. So let me make that formal. So I start with UN, which is the unitary group in n dimensions. I consider a matrix U, which is in this group. But I now impose a condition that its determinant has to be equal to 1. So this must be a subgroup. Now, I will later prove that it is a subgroup. It's certainly a subset of all U's, right? Because I take any U, I calculate its determinant. It could be 1, it could be something else. I only consider the subset whose determinant is 1. So I write U as e to the it. Now, there is a theorem in matrix algebra that the determinant of e to the a is e to the trace a. I don't know. How many of you don't know this theorem? Okay. Now, we'll let the mathematicians give you a rigorous proof. But it's easy to imagine why this may be the case. I mean, in physics, for a physicist, it's more important to be able to imagine why this is the case through some non-trivial examples rather than to give a rigorous proof, all right? Suppose A is a Hermitian matrix. Now, here it's not a Hermitian matrix. It's I times a Hermitian matrix. But even with an I, it's easy to prove. But for simplicity, consider it's a Hermitian matrix. If it's a Hermitian matrix, that means you can diagonalize the matrix, right? So let me go to a representation in which A is diagonal. I will prove this in the representation in which A is diagonal, okay? Now, determinant of e to the a. What is e to the a? Well, A would be equal to A1, A2, and so on. It would be diagonal matrix. So e to the a would be the matrix e to the a1, e to the a2, and so on, right? So the determinant of this is just this product, because if you apply something like the Cramer's rule, this is the only non-zero one, right? So e to the a1, e to the a2 is e to the sum of the a's, which is e to the trace a. All right? So it's a trivial, relatively trivial statement for a Hermitian matrix. And in fact, this is all we need, because in our case, A is a I times a Hermitian matrix, right? So it's really IA. Right? Our A is I times a Hermitian matrix. So if I can diagonalize A, I can diagonalize IA. So this proof actually works as far as we need. But it's actually more general. Even if A is neither Hermitian nor I times Hermitian, it's still true. And leave that to the mathematicians, right? So if you think about it in these terms, it's actually a trivial theorem. So if the determinant of, so the condition was determinant EIT is 1, using this theorem, I have e to the trace of IT is equal to 1. Okay? Just e to the trace of IT. Now, e to something is equal to 1. That means the exponent is 0. So trace of IT is equal to 0, or trace of t is equal to 0. Okay? So to say that U has determinant 1 is the same as saying that the t upstairs has 0 trace. But I better check whether this is a subgroup. So if U has determinant 1, V has determinant 1, and I take their product, then determinant of W is just the determinant of the product. So if I start off with 2 of them, each of which has determinant 1, the product also has determinant 1. So the subset with determinant 1, subset, is actually a subgroup, okay? Because I can take a subset of a group, it need not be a subgroup unless it's closed under multiplications. So this subgroup is called SUN. S stands for special. It's called the special unitary group in n dimensions. Okay? So it's the set of unitary matrices with unit determinant. And the corresponding algebra, if I take the t in the exponent, involves traceless Hermitian matrices. And again, there is some typographical errors. Why don't you note down and tell Yu Wenlong to change it all? Oops. The upper limit should be n squared minus 1. The lower limit should be 1. This is very important. Lower limit is 1, not 0. Okay? So it excludes the identity. Now, why are the others okay? Now, T0 is the identity, so the trace is not 0. How about the others? How do I know the trace of the others are 0? Because I define the trace of TATB to be delta AB, right? Because I chose an orthogonal basis in this sense. So if I take a case where B is equal to 0, then this is 0 for A not equal to 0. Right? But T0 is just the identity. So all the other T's have 0 trace. Okay? The orthonormal requirement automatically guarantees that T1, T2, all the rest have 0 trace. So as a summary, SUN consists of all U's that can be written as this exponential form, where the theta A's ranging over this number are real numbers, like angles. And the TA's, again, ranging over this range are Hermitian matrices, where the TA's satisfy this choice. And this is, you see, a generalization of something we learned about rotations, where the rotations are e to the I theta times j. Theta are three numbers, in that case, with three components, that specify a vector in three-dimensional space, the axis and the angle rotation. And the three j's are the Hermitian matrices. And in fact, in that case, if you look at the Pauli matrices, the trace of JA, JB is, well, in that case, a factor of 2. If you put a factor of 2 here, that just redefines the theta by a factor of 2. Doesn't matter. So this is the group SUN. It is a generalization of the rotation group, where the rotation group can be regarded as swapping two things. It's SU2. It has n squared minus 1 generators. Okay? When you swap n things, you have n squared minus 1 generators. So, for example, in SU3, there are 8 generators, 9 minus 1. Okay? And I believe in one of the exercises, I asked you to calculate some of the generators, express some of the generators of SU3. So just to remind you about the n equals 2 case, the number of generators, n squared minus 1, would be equal to 3. So the three t's would be called T1, T2, T3. They are just the same as Jx, Jy, Jz. And the matrices are, of course, just the Pauli matrices. And you can check that the trace satisfies the same. Now, in the final 15 minutes or so, I will now introduce the algebra. Because up to now, I have not talked about the commutation among the t's. Right? I've told you you have to add the t's and so on, right? Trace is 0, but I have not talked about the commutator. Now I talk about the commutator. In general, the u's do not commute. And the word we use is non-abelian. Okay? This forms a non-abelian group. A group where multiplication does not commute is said to be non-abelian. And if you look at this property in terms of the t's, the corresponding properties is that the t's do not commute. And we say this is a Lie algebra. So let's look at the commutation between two t's, because that's all we need to understand. Now, the first t can always be written as theta a t a. That is expressing this, which is an element of the linear space in terms of the basis. Okay? Any t, any Hermitian traceless matrix, can be written as real numbers times the basis matrices. The second one can be also written like this with a different set of parameters. Sum over A, sum over B, of course. So this commutator then becomes theta A, theta B prime, T A, T B. These are just parameters. So all you need to know, all I'm saying in this slide, is that all you need to know is the commutator among the basis, T's. Okay? So go back to the case of rotations. Any rotations can be written as theta times j, another rotations, another set of theta times j. So the commutator between two rotations, all you need to know are commutators between JA and JB, say JX and JY. So let's investigate JA commutator JB. My first claim is that this is an anti-Hermitian operator. How do I know this? So, this is wrong. This A, this should be. I think Yuan Long mounted the wrong slide. I have all these corrected already. Anyway, doesn't matter. So TA, TB minus TB, TA. That's the commutator. I take the Hermitian conjugate. But when you take a Hermitian conjugate, you take the conjugate of each and then reverse the order, right? So TA, TB conjugate is TB conjugate, TA conjugate. But each T is Hermitian. So TB dagger is TB, TA dagger is TA. But what is this? This is minus the commutator, right? Because that's the commutator reversed. So this thing, dagger, is equal to minus itself. So it's anti-Hermitian. Secondly, this commutator is traceless. How do I know? Well, commutator TATB is just this bracket. But the trace of this is 0 because the trace of AB is the same as the trace of BA. When you have a trace of a product, you can do a cyclic permutation. Okay? So this is again traceless. So if TATB is anti-Hermitian and traceless, I can always write it as I times another member of the linear space. That is I times another Hermitian traceless matrix. Okay? So if it's another Hermitian matrix, it can be written as a sum over the basis matrices TC. Sum over C. So commutator of TATB is a linear combination I times TC, and these coefficients are called FABC. Sum over C implied. These are called the structure constants of the Lie group. SU2 case, these are just epsilon ABC. Okay? So once you have defined a basis, by calculating the commutators, you can find the structure constants. The structure constants is a set of real numbers carrying 3 indices, each of ABC ranges from 1 to n squared minus 1. So let's check. How many structure constants are there for SU3? For SU3, n squared minus 1 is equal to 8. So f of ABC, each of ABC has 8 choices. So there are 8 to the 3 structure constants. Okay? Now, of course, many of these are 0. For example, if A and B are the same, of course, this is 0. They are also related by certain permutations and so on, some of which I will come to in just a minute. Okay? The first property is that the structure constants are cyclic. That is, if I do a cyclic permutation of ABC, it's the same. That is something you may have guessed from the example of SU2. Epsilon ABC is cyclic, right? Now, how do we prove this in general? I need to write one more line. TATB is equal to IFABC TC. Now I multiply by TC and I take the trace. Okay? Now the trace of TC with TC is 1. So that gives me this line, that IFABC is a trace of TATB commutator multiplied by TC. Right? So let's write it out. This is TATB and minus TBTA. But I use the fact that a trace is cyclic over the factors. So ABC, I can write it as BCA. BAC, I can write as CBA. Right? Trace ABC is equal to trace BCA and so on. That's a theorem in matrix multiplications. And this bracket, because TA is on the outside at the end, so it is actually the commutator of TB with TC multiplied by TA. And if I compare this with the first line, I see the left-hand side is actually IFBCA. Okay? So that shows F is cyclic. Secondly, I claim that F is totally antisymmetric. And let me just prove one example. I want to prove in this case, for example, if I hold the first index fixed, I want to prove that the second and third index, I goof something. What did I goof? Let me see. Oh, I missed the minus sign, but I'll tell you later. I want to prove that if I interchange the second and the third index, they differ by minus sign. Now, because to prove that the first two indices are antisymmetric is trivial, because those two indices are related to the commutator. So if you change them, that just changes the commutator by minus sign. It's less trivial to prove that the second and third, for example, are antisymmetric. But the trick is to use the cyclic property to move them to the first and second place. So using the cyclic property, CBA becomes BAC. But if I change BA to AB, interchange the first two, there should be a minus sign. Okay? Now I use a cyclic to change it back. Okay? So the second and third indices, if you interchange, is antisymmetric. So these two properties are, you could have guessed from the SU2 case that the epsilon factor is cyclic, totally antisymmetric, and that those properties are preserved in the generalization to SUN. Okay, so that's all. This is just a mathematical tool that you need when you want to discuss swapping more than two objects. Okay, and the physical example, the most important one, is swapping the three colors, red, green, and blue. So if you want to swap the three colors, or if you want to swap the three flavors, you have to discuss the group SU3. And this is the formal structure, which is a generalization of the rotation group. Okay. Any questions?
What's the physical meaning of the number of generators, and what the relationship between that number and the number of states of the system?
Oh, the number of states can be huge. Absolutely nothing to do with it. Go back to SU2. There are 3 generators, but you can have L equals 20, which would have 41 states. That's the size of the representation. It has nothing to do with the size of the number of generators. Later, we will show, in the case of chromodynamics, the number of generators is equal to the number of gluons. Number of gluons. Okay? Number of analogs of photons. In mathematical terms, is the number of connection 1 forms. For those of you who've taken general relativism, a number of Christoffel symbols. And just to jump ahead, so that you don't lose count. You remember the Christoffel symbols, for those of you who have studied these things, carries 3 indices, all right? Still remember, those of you who studied relativity? From this point of view, we'll show later